Good afternoon and welcome to our ARC webinar on OPC UA TSN and the future of industrial networks. My name is David Humphrey. I'm an analyst with ARC Advisory Group, and I will be moderating and giving part of the webinar today. I am joined by my colleague Frank Thomas, a consultant here at ARC Advisory Group. Frank will present part of the presentation and he'll handle the Q&A at the end as well. What we're going to talk about today is what we see as happening right now in the area of industrial networking and what we think is going to change, how that's going to affect the development of industrial networks in the future. I'll start off with a brief look back to see how we got here and what's happened up until now. Then we'll look at two specific technologies, OPC UA and TSN, and we'll discuss their impact on industrial networking as we see it. And then we'll take a look ahead and see what we think or where we think things are going to go in the future with this technology. So what's happening in industrial networking? I can never tell the story without giving a little bit of background. Going way back to the 1980s, there were at the time still competing standards for networking in the rest of the world, in the commercial area, banking and insurance companies, universities, etc. The rest of the world solved the problem in the 1980s by agreeing that Ethernet should be the standard and that the IEEE should maintain the standard and develop it in the future. In the industrial world, Ethernet was considered at the time as well, but it was thought to be not suitable for applications in manufacturing and the process industries because of issues with timing, because of the lack of determinism. The result was that individual companies developed their own industrial networks that we had in the 1990s. And then in about 2004, our industry once again realized that we've got to do something to make ourselves modern, that with the advent of the internet and the need for connectivity in the plant, we really need some sort of network that's at least based on Ethernet. So the result was that at least 6 and probably more different versions of what we call industrial Ethernet were developed. They were backed by large suppliers who sought to gain some sort of advantage for them, even though these networks were given to the rest of the world as quasi semi-open networks. The problem is that these 6 different flavors of industrial Ethernet were for the most part not compatible with each other and didn't really help solve the problem of focusing on the application rather than on the infrastructure or the technology. Let's fast forward to today. What do we have today? The rest of the world, I call it the IT world, but also the telecoms, long ago agreed on standards, not just Ethernet, but also for telephone communications between countries. There's only one standard out there. In the meantime, even though we thought that industrial Ethernet for us was finished, we're now confronted with 2 new technologies that are promising to maybe help unify Ethernet in the future as it's used in industry. Those technologies are OPC UA and TSN, and we'll talk about those in greater detail in just a few slides. What we have today is more or less open, compatible controller-to-controller communication if you use OPCA, but we don't have any sort of unifying communication using OPC UA that goes down to the field device level, so the classic I/O level. A single solution, were it to come, would have the effect of consolidating these 6 or so different versions of industrial Ethernet into one, creating just a single solution. And like I said before, would simplify things by taking the focus away from which technologies we're using and allow us to concentrate once again on what's important, the application. So what should the future of industrial networking look like? Our vision here at ARC is that in the future, there should be and will be only one Ethernet that is used by industrial companies. This Ethernet will be a part of the IEEE 802.3 standard Ethernet specification, and for that reason, everything that is Ethernet will automatically benefit from improvements and developments and enhancements as they're made. That means if we use 100 megabit Ethernet today, and Ethernet goes to gigabyte or 10 gigabyte or something beyond that, then the rest of the industry can simply grow with Ethernet and doesn't have to be stuck in some sort of old specification that restricts the speed. It will incorporate the 2 technology that I mentioned, OPC UA and TSN, as part of the standards, the network will continue, and this is very important, to support the current legacy protocols, because if we don't promise this, if we don't guarantee this, there's no way we can move on to new technologies. We have to protect the investment in the installed base that has been going on for the past few decades. Industrial companies in the future will and should have influence in the IEEE to help represent the interests of industry and not just the commercial companies in the development. And finally, and this is important too, and I'll get to this point later, industry will work together to create a multitude of companion specs for all devices and applications. What's a companion spec? I'll talk about that later, but it's really the meat of the infrastructure. If you consider the network and the hardware that things run on, what's really important is the software that runs on top of that, not the hardware. And the companion spec describes the way information is to be called and communicated in specific applications. Basically, it's a set of semantics that apply to different specifications for robotics, for RFID, for a huge variety of different applications, and is extremely important to the success of this model in the future. So briefly, what is OPC UA? I think a lot of you might be familiar with this. I'll just go briefly over a couple of definitions so we agree on everything. OPC is a specification for a client-server model of communications that's over 20 years old. It was first published in 1996. The UA part of it is a unified architecture that came out over 10 years ago and removed the dependence on the Microsoft platform of OPC and made it platform independent. Now I'm going to skip over some parts of OPC and get right to the important thing that we'll talk about today. There are basically two ways to communicate using OPC over networks. One is peer-to-peer, and peers are the smart devices like controllers or IPCs that sit at a certain level in the factory and communicate with each other information, but not necessarily time-critical information. For example, PLCs of two different manufacturers should be able to exchange blocks of data, for example, recipes in a production line in food and bev. The other way to communicate is from a controller down to its slave devices. These could be field devices, I/O, these could be drives, anything out there on the machine. OPC UA uses what they call a pub-sub model that I'll describe on the next slide to communicate in a time-critical fashion with I/O devices. If you're a typical manufacturer, you might be stuck with the problem that you have controllers in your factory on your machines from different manufacturers. Here's a typical case. On the left-hand side, we have a Siemens architecture. On the right-hand side, we have a Rockwell architecture. Each has its own field devices, and those are connected to the controller with the corresponding version of industrial network that fits the philosophy of the company. In the case of Siemens, it's Profinet. In the case of Rockwell, it's Ethernet IP. Today, it's possible to communicate between controllers using OPC UA. In the past, the controllers could communicate because they both understood Ethernet, but they spoke different languages. There wasn't a common language for them to communicate. It's like calling a relative in Beijing. You can make the telephone ring in Beijing, but it doesn't mean you can speak Chinese or the other way around. OPC UA is this communications protocol that all devices are capable of speaking because it's neutral, and it allows all devices to communicate with each other. Now, what happens if we want to do the same thing at the device level? And this is where things start to get political, because there is a lot of interest in protecting the installed base and even the future installed base by some of these suppliers, including these two on the screen. In the future, it would be nice if, for example, that I/O device in the lower right-hand corner that is a Rockwell device, the one that has a little bit of red around the fringe. What if we wanted to send data from that device to the Siemens controller? Well, one way would be to send the data first to the Rockwell controller directly above it, and then communicate those data via OPC UA to the left over to the Siemens controller. That would be nice, but that wouldn't be very time critical. We just don't have the speed or the protocol capable of handling anything very fast. One way of doing it would be to use the already finished and published model that OPC UA calls PubSub. PubSub means that that device down there in the right-hand corner publishes data. It could be a small amount of data. It could be 2 or 3 words of data. It publishes data by putting those data onto the network at a certain time interval. Let's say we need data pretty fast, so every 5 milliseconds, which is pretty fast. If data are published, that means that they can be seen or subscribed to by other devices. So a Siemens device, also supporting OPC UA, could be configured to look out and see what data are available and say, there's some data, 3 words from the Rockwell device. I'm going to subscribe to those, and I'm going to receive those data automatically. It's technically capable today, but our question that we'll try to look at and maybe even answer in a few slides is, can this model, this communications protocol PubSub, be used for all I/O devices and replace the 2 networks you see here, the one in green and the one in yellow. I'm going to turn the baton over to Frank to go into a little bit more detail to help us understand exactly where OPC and TSN sit in the network stack. Frank?
Yes, very important to understand is that OPC UA is just one of many other protocols sitting in the ISO-OC layer model on the levels 5 to 7. And as David pointed out already, the most important thing, which is the description of the semantics in the OPC UA companion specifications. Let's say a plastic injection machine talks a certain language, which is tied to the plastic injection machine. That is all laid out and coordinated in the companion specifications. And so over the time, more and more companion specifications for more and more devices will come up in the future and define what language you talk if you talk to a certain machine. That has in the past not been a part of the ISO-OC layer model, and I just put it above. It sits above there, and is a great help to talk the right language without any translation in between. I think we'll have a slide for TSN as well, but you see on this, yeah, here it is. Important to understand is TSN is on the layer 2 and provides deterministic services, which you'll see above there on the slide, with guaranteed package transport time, latency time, and low package delay variation. It's not a complete communication protocol, but it is a transportation technology for communication. We'll come to this later. TSN is a bundle of standards within IEEE, so there is not just one single standard. And here you will find in the world of TSN users that one TSN user may use 4 or 5 of these standards, and the other may use 7 or 8 of these standards, depending on the application. But we can come to this on a later slide.
So we've discussed about the 2 major technologies and their potential, what they can possibly offer. But what is standing in the way? What are some of the barriers to overcome before we adopt, in this particular case, TSN in field buses? Today, not all, but many field buses use chips for real-time performance. There are some that use standard unmodified Ethernet, and there are others that use Ethernet that is modified. One example is Profinet. To take advantage of the IRT timing mechanism, you need a special chip in each device. Every single device in that segment of the network has to have it, otherwise the synchronization doesn't work. To incorporate TSN, obviously these designs would have to change and include the TSN functionality. And before we can start production of the chips, these TSN standards have to be finished, completed, signed off, and available.
As I just pointed out, the TSN is a bundle of standards. There are already chips available. with a certain selection of standards, but we also see quite a couple of FPGAs because companies think that they may later inject other standards once they are published. So there are chips available, but this is an ongoing process of improvements and enhancements depending on which TSN standards are finalized and published.
It sounds like we are saying that TSN functionality is better than anything we had in the past, but really until there's some clear benchmarks and comparisons, we're not necessarily saying or claiming that TSN is any better. And some of the experts out there are starting to say there are certain applications where the existing technology might not be standard, but it's faster. So there has to be a lot of clarification and some testing done to really prove for which applications particular TSN is suitable. Other considerations are everything that it surrounds our industrial applications. There are all sorts of protocols and requirements like in safety or for use in explosive and hazardous environments that require certification and approval from certain authorities. And for this reason, we expect TSN to be implemented also independently of OPC UA by most of the field bus organizations. They're working on it already. They're very, very conscious of it. But implementation is one thing, and adaptation is another thing. And we expect the adaptation to take a number of years. Our feeling is that things might get going in 3 to 5 years. I want to move into the political spectrum of this technology discussion. This is a little bit more sensitive area because we know from the past that there are certain commercial financial interests in having technologies work certain ways to support your particular goals of a company. We mentioned before about the OPC Foundation being a neutral, open organization. Anybody can be a member in it. There is an organization that was just founded last year that's not really officially an organization yet. It's called the Shaper Group. It's made up of the companies listed below from ABB down to Vago. After its founding about halfway through last year, one of the major suppliers, Rockwell Automation, joined the organization and threw its weight in this direction. Member companies want to implement OPC using TSN from through the entire spectrum, not just the device level, sensor actor level to the controller, but right up to the cloud, which means the implementation of not just our standard protocols, but some other existing open communication protocols. There are already a number of demos going on showing the progress of the member companies. The Shaper Group has been formed as sort of a lobby organization to push things along faster, and that's what's the really important differences right now. What's the need for a Shaper Group? We're not the people to ask. The Shaper Group itself made an appearance last year at the SPS IPC Drives Fair in Nuremberg, and will probably make another appearance again, maybe a press conference. We expected an announcement with some sort of more organizational information to come this fall, but nothing has materialized yet. But I do want to take a look in one later slide at exactly what the different philosophies are, because we're starting to see a split in the philosophies. Before I get to that, and before we wrap up and get to the Q&A session, I just wanted to show a quick slide on what a companion specification is. I want to emphasize the importance of this. The companion specification is a description of the information model, including a lot of different data types that describe functions and features of an object. This could be a simple sensor, or it could be something as complex as a controller or a robot. The companion spec also unifies the language. It unifies the semantics used to communicate information back and forth so that the different suppliers don't use their own version of the language. Everybody's speaking the same language. This is really critical and really cuts through a lot of red tape if you're trying to engineer a system. If you want a comparison, the closest thing I can think of is to the batch specification, the batch standard, I should say, that was standardized by ISA maybe over 20 years ago. that allowed the entire batch control industry to use the same device models and equipment models and speak the same language and cut through a lot of engineering. At the bottom is a quote that emphasizes the importance of this by Heinrich Munz, our friend from KUKA Robots over in Augsburg. The companion specs are semantic self-descriptions for machines in the focus of EDMA and are the link to connect the OT world with the IT world. That's what makes Industry 4.0 really possible. This, again, like I mentioned before, is the real content of the whole model of a new industrial network solely based on Ethernet and augmented with OPC UA and TSN technology. The big question is will this replace the existing Ethernet-based field buses as we know them? Well, the top level is done. The controller-to-controller stuff is finished. We can use standard Ethernet there, and nearly every device on the market today supports peer-to-peer communication using OPC UA. The question is what will happen at the field level? And I have to mention that there are two, let's go to the next slide actually, in the interest of time, that the two camps, two schools of thought have emerged right now. I've given them my own names. I call the first group Slowly But Surely, and the second group, Let's Do It Now. In other words, let's do it faster. The conservative group on the left-hand side is in agreement that we should have one network for everything, but we should do things step by step, that there's a lot of clarification still to be done at the peer-to-peer level, and there's no need to dive into trying to solve the problem by next year by incorporating the field device level. The first priorities there are finishing standardizing the acyclical communication for machine-to-machine to MES, to industry software, and up to the cloud. And also to finish modeling descriptions of interfaces through companion specs. There's a lot more companion specs still yet to be written. And then using this model as a basis for the development of companion specs for field devices using cyclical communication. In other words, OPC UA pub sub. For TSN, they say it's necessary to first achieve a convergence at layer 2 before we start with substitution of field bus protocols that will run using TSN. And that includes things like agreeing on how traffic is fed into the internet and where these configurations are stored. Are they stored locally? Are they stored in devices? Are they stored remotely somewhere in the cloud? And then all of these factors will play a big role for the companies that eventually develop chips for devices that understand TSN. And finally, what's the future role of these field bus organizations? This is the group that claims that there are some apps out there that actually might run better still on existing field buses. So there's room for the coexistence in the future of both. As long as the industry is calling for devices with certain specifications, then the thinking is that we should support them. On the other side, we have the Shaper group, with the members that I mentioned. Their goal is to convince the OPC Foundation to promote consistency within OPC UA from the cloud down to the field device level, and to develop in a quick fashion to really make a break with the past, develop the end-to-end communication solution, fulfilling the concept of the automation pyramid. And there's no clear statement because the organization is still very young and hasn't really communicated a heck of a lot, but likely that they'll also continue to support the field buses as long as necessary. That's simply what we do in this organization and how things work. This is the end of the presentation to give an overview on OPC UA, TSN, and their effects on the future of industrial networking.